And this is Math 131, section 10.1. In this chapter, first section, we're going to talk about groups. But first, let's define what a mathematical system is. So, a mathematical system, okay, consists of a set of elements, okay, like a set, and at least one binary operation. So let's define what that means. Okay, a binary operation is an operation or a rule, okay, that can be performed on two and only two elements of a set, okay? And then the result is a single element, okay? So think of like addition. You know, we take addition, we're going to take two elements and add them, okay, and get like 2 plus 3 equals 5. We get one element back. Multiplication, 2 times 3 equals 6 would give us one element back. Subtraction, 2 minus 3 would be minus 1. We get one element back. And division, 2 divided by 3 would be 2/3, right? Which is 2/3 or 0.666 repeating, right? These are all binary operations, okay? Okay. So like the set of integers and the binary operation of addition makes up a mathematical system. So that's an example of a mathematical system where we have our set of integers is our set, okay, and the binary operation would be adding, right? So there's an example. Okay, so let's talk about the commutative property for addition. We've already looked at this in the previous chapter, but we'll kind of look at it in the context of groups. Okay, so for any elements A, B, and C, okay, addition would say the commutative property says A plus B equals B plus A. If you switch the order of adding, it's still the same. And multiplication, A times B equals B times A. Okay, so there's a commutative property. Okay, associative property. Okay, for elements A, B, C. Addition, A plus B plus C, where we add A and B first, is the same as A plus B plus C if we add B plus C first. So if we regroup our addition, it doesn't change, right? And then multiplication, A times B times C if we multiply A times B first is the same as A times B times C if we multiply B times C first. So here you're adding A and B first for addition, and here you're adding B plus C first. It doesn't matter, right? Here you're multiplying A plus B first in multiplication. Here you're multiplying B times C first. Again, you get the same answer. Okay, and we looked at this for numbers before. Okay, and again, let's look at the concept of closure. I talked about this a little bit earlier too. If a binary operation is performed on any two elements of a set, okay, and the result is an element of a set, so this is an important part, so let me put that, the result is an element of the set, then that set is closed, okay, or has closure under the given binary operation. Remember, binary operation means you just have two elements, okay? So this is the important part. The result is an element of the set. Okay, so that's the key. That whatever results we get something that's still in that set. And that's how we determine whether we have closure. If we get something that's not in that set, then we don't have closure. Okay, now let's talk about the concept of an identity element. Identity element is an element that when a binary operation is performed on it and any given element in the set, the result doesn't change. The result is the given element. Okay, so for example, identity element for addition. If I start with 2, all right, go back to my fine point here. If I start with 2 and I add 0, I get 2 again. See, I'm trying to get back to where I started. So if I add 0, I get 2, right? If I multiply 2 times something to get 2, I have to multiply times 1. So that's my identity element for multiplication, okay? So here's your identity element for addition. Here's your identity element for multiplication, okay? So we can say the additive identity element is 0. That's the identity element for adding. The multiplicative identity element is 1. Okay, inverses. When a binary operation is performed on two elements in a set, and the result is the identity element for the binary operation. Okay, each element is said to be the inverse of the other. Okay, so for example, for addition, if I want to add something to 2 and I want to get my identity element, right? I'll put a box around that because that's what we're trying to get. Then I have to add a minus 2, right? So that's the inverse. That's called the additive inverse of 2. Okay. If I want to take 2 and multiply it times some number to get my identity element. Now here my identity element is 1, right? Because I'm multiplying. Okay, so I need to multiply it times a half. So that's called my multiplicative inverse. So we have 2 different types of inverses based on these 2 operations. Our additive inverse is going to be just change the sign of the number from 2 to -2, or from minus a half to a plus half, or -3 to +3, or 5 to -5. But if you add those, you're going to get 0, which is your identity element for addition. Okay. If we multiply, we have to take the reciprocal, right? We have to take 1 over the number to get the inverse. Okay. So if I have 2 and I want to get to 1 by multiplying, I have to multiply 2 times a half. If I had like 2/3, I'd have to multiply times 3/2, right? So this is our inverse element for multiplication, is the reciprocal of the 2. Okay. So again, additive inverse is just change the sign. Multiplicative inverse is take the reciprocal, flip the fraction. Okay, so just to summarize, the additive inverse of a non-zero integer, it can't be 0. Okay, a is minus a. Okay, 0 is its own additive inverse. That's why we don't use minus a. Okay, but it doesn't. If you think of -0, it's still 0. Okay, the multiplicative inverse of a is 1 over a. Okay, reciprocal. Okay. However, it may not be an integer. Okay. So we can say that most integers do not have a multiplicative inverse in the set of integers. Okay. In other words, in the set of integers, if I start with 2 and I have to multiply it times a half to get to my identity element, right? Well, this half is not an integer. So we can say it doesn't have a multiplicative inverse in the set of integers because 1/2 is not an integer. Okay, and this gets us to the concept of a group. So we're going to talk about the properties of a group. Okay, so we have a mathematical system, which we already defined, right? A set and a binary operation. Okay, and it has to have 4 requirements to be called a group. Okay, so there are 4 requirements. Okay, so the 4 requirements are this. Number 1, let me number these so you can see where they are. Here's 1. Here's 2. Here's 3, and here's 4. Okay, so there's 4 properties we're looking for. Okay, so the first one is the set of elements is closed under the given operation. In other words, if we say our operation is plus, any 2 elements that we add, we're going to get an element that's still in our set. Okay, if we're multiplying any 2 elements that we multiply, the answer would still be in our set. So we need closure. Okay. We have to have an identity element in the set, okay, under the given operation. We just talked about that, okay. Has to have an inverse in the given operation. So the inverse has to be in the set. And finally, the set of elements is associative under the given operation. Okay, so we'll look at that too. So we'll look at the associative properties. So 4 things, okay. We have to have, number 1, we have to have closure. We have to have an identity element, we have to have an inverse, and we have to have associative property work for any 3 elements. Okay, so that defines a group. If we want to have a commutative group, then we have to have 1 additional requirement. So this is our additional requirement. We have a group, and it also satisfies the commutative property. Okay, and we call that a commutative group. So the commutative group requires 1 extra step. We have to have the commutative property as well. Okay, so that's sort of our 5th requirement. Okay, so I'll put a 5 there, and this would make it a commutative group. Okay, so the group has to satisfy the commutative property as well. Okay, so for a commutative group, we have to have all 5 conditions, which is number 1, the set of elements is closed under the given operation, so closure. We have an identity element exists for the set, for the given operation. Every element in the set has an inverse under the given operation. Okay. The set of elements is associative under the given operation. And then finally, that last thing, the set of elements is commutative under the given operation. So we have to have all 5 of those apply to have a commutative group. So think of it as a group that also has a commutative property, and that's the 5th requirement. Okay, so let's look at our first example. We're going to look at the set of whole numbers under addition. So determine whether the mathematical system consisting of the set of whole numbers under the operation of addition forms a group. Okay, so the first thing we look at is closure. We take the sum of any two whole numbers and see if it's a whole number, right? If it's still in the set. And this is closed. Anytime we add two whole numbers, we get a whole number. Okay, so that's closure under addition. So we have closure, check. Okay, put a little check mark there. Okay, identity element is 0. We need 0, right? Because that's when we add 0, we get the same number, right? Is 0 in our set of whole numbers? Yes, the additive identity. So the system contains an identity element. Okay, check, we're good with that. Okay, inverse element. Okay, do these have inverses in the set of whole numbers? Okay, remember the additive inverse is the opposite of the number. Okay, -1 is the additive inverse of 1. -2 is the additive inverse of 2. Okay, so the numbers 1, -1, -2, which we need, are not in the set of whole numbers. Okay, so the mathematical system is not a group. So we can stop here because we don't have an inverse element, right? See, we need to add -1 to 1 to get 0, right? In other words, 1's inverse is additive inverse is -1, but it's not a whole number. So if they're not in the set, we don't have the inverse elements in the set, for an example, then we're done. We can say, no, it doesn't have an inverse. So that's in the set of whole numbers. So we can say this is not a group. Okay, so this one is not satisfied, and we're done. Once we get to one of the qualifications that are not met, we can stop. Okay, now let's look at the set of real numbers under the operation of addition, and to see if that forms a commutative group. Okay, so we want to check 5 things for this one. Okay, so we check closure first. The sum of any two real numbers is a real. We should be a real number. Okay, so that should be a real number there. Okay, we're talking about real numbers, so it doesn't have to be a whole number. It just has to be a real number. Okay, and that is true. Okay, so we're good with that. If we take the sum of any two real numbers, it is a real number. Okay, so we have closure under addition. Okay, that's a typo. There shouldn't be a whole number there. Okay, identity element. Yep. 0 is the additive identity element. A plus 0 equals A, or 0. The system contains an identity element because 0 is part of our real numbers. So first qualification met, second is met. Okay. Okay, inverse elements. Okay, we're talking about additive inverse because we're talking about operation is addition, right? So remember the additive inverse is the opposite of the number. So -1 is the additive inverse of 1. Minus A is that of A. A plus minus A equals minus A plus A, which is 0. Okay, and we can say, yeah, those are all real numbers, right? So all real numbers have an additive inverse. So for example, if I have 3, I have to add -3, right? Well, that's a real number, right? If I have -2/3, I have to add +2/3, right, to get 0. So is this thing a real number? Yep. Is this thing a real number? Yeah. So, and we can say that for pretty much any real number that you add, you have to add the opposite, right? Okay. So yes, if A is a real number, minus A is a real number. So we say we do have the inverse element. Okay. Okay. Now we have to check the associative property for any real numbers A, B, and C. If we add the first two and then add the third, is it the same as adding the second and the third and then the first? Yeah, that's true for any real numbers. So we know the associative property works, right? And finally, commutative property for real numbers, adding. Okay, so for any real numbers A plus B, we have A plus B equals B plus A. That's true for our real numbers. So we can say the set of real numbers forms a commutative group. Now we have to say under addition, right? Under, because that's our, remember, we have to have an operation, and we're talking about addition here, right? Okay. So it should say the set of real numbers under addition forms a commutative group. Okay, so we have to have an operation, and our operation is addition. Okay, okay, so we'll look at some other examples where we have a commutative group and somewhere we don't, or we have a group and somewhere we don't. In this case, we have a group that also has commutative properties, so it's a commutative group. Okay.